If f of x equals the square root of x minus 1 and g of x equals x squared plus 2, find f of g of x and g of f of x and their domains. First, let's look at the domains of f and g by themselves. G is pretty easy because it's a polynomial. We end up with all real numbers for the domain. So that's easy. F requires just a little bit more work. We've got a variable inside a radical, and so we need the radicand to be greater than or equal to 0. So x minus 1 has to be greater than or equal to 0. Adding 1 to both sides, this gives us x is greater than or equal to 1. And so the domain here is going to be the set of numbers x such that x is greater than or equal to 1. This is going to come into play later on. So let's start by looking at f of g of x. Here we have to evaluate f at g of x. But if we look at g of x, g takes x as an input and gives us x squared plus 2 as an output. So this is going to be f evaluated at x squared plus 2. Now, if we look at the function f, what it does is it takes the input, it subtracts 1, and then takes the square root. So here we've got to take the input, x squared plus 2, and then subtract 1, and then take the square root. Effectively, what we've done is, in our function f of x, we've replaced x with x squared plus 2. So we've got, instead of the square root of x minus 1, it's the square root of x squared plus 2 minus 1. Now we can simplify the inside there because 2 minus 1 is just 1. So this becomes the square root of x squared plus 1. Now, we need to look at the domain here, and to do that, we need to examine what happened in this composition. So we started with x, and first g acted upon x to give us x squared plus 2, and then f acted upon that to give us the square root of x squared plus 1. Now, we need to make sure that x is in the domain of g, and that x squared plus 2 is in the domain of f. Because the domain of g was all real numbers, we don't have any problems substituting an x because all values will work. But things are different when we look at f. Remember, with f, we needed the input to be greater than or equal to 1. The domain of f is that the input has to be greater than or equal to 1. Well, if the input here is x squared plus 2, this requires that x squared plus 2 is greater than or equal to 1. Because if we have anything in here that's not greater than or equal to 1, if we've got something that's less than 1, we're going to end up with an undefined result. So we need to make sure that we're picking x values so this is true. Now here, if we subtract 2 from both sides, this gives us x squared is greater than or equal to negative 1. And we've seen this inequality before. We know that this is always true, because anytime we square a number, the result is either positive or 0, and all positive numbers and 0 are greater than negative 1. So this is always true. And so the domain here will also be all real numbers. And so because we don't have any problems plugging in anything for g and then having that go into f, our domain for the composition of functions is also going to be all real numbers. So in the end, our composition is going to be f of g of x equals the square root of x squared plus 1. And the domain is going to be all real numbers, which we can write in interval notation as negative infinity to positive infinity. You could also use set builder notation if it's not specified. Like here, we don't actually specify, but if you're using WebAssign or some homework system that does specify, you have to choose the method that they want. Now let's take a look at g of f of x, the other composition. We have to evaluate g at f of x, and we know f of x is the square root of x minus 1. So here we've got g of the square root of x minus 1. Now g as a function takes the input and squares it, and then it adds 2. So we have to take the input, which is x minus 1, and then we have to square it, and then add 2. Now, when we take the square root of x minus 1 and square it, we end up with just x minus 1. The reason for this is because squaring something is the opposite of taking the square root. Right, if we took the square root of 9, we'd get 3, and then if we squared 3, we would get 9 back again. If we started with 25, taking the square root gives us 5, and then squaring it gives us 25. So whenever we square something that's underneath a square root, the squaring and the square root cancel, and we're left with just the radicand. Here, that's x minus 1. And then, of course, we still need to add 2. Now, when we combine these constant terms, negative 1 plus 2 is positive 1. So in the end, we end up with x plus 1. Now, if you were to just look at this as a function, you might think that the domain is going to be all real numbers, because x plus 1 doesn't have any radicals or fractions. It looks good. However, because this came from a composition of functions, we have to look at each step of that composition. And we're going to see that the domain is not all real numbers. So let's look here. First we start with f, and then, first we start with x, and then f acts upon it to give us the square root of x minus 1. And then afterwards we put that through g, and then when we take the square root of x minus 1 and we square it and add 2, we end up with x plus 1 as our final output. Now, the domain of G is all real numbers. We saw that in the very beginning. So we don't actually have to worry about this part of the machine. It's this part of the machine that we have to be concerned with. And if we look for the domain of f, the domain of f is the set of numbers greater than or equal to 1. So we need the input to be greater than or equal to 1, which means x has to be greater than or equal to 1. The domain is not going to be all real numbers, because if we pick something that's not greater than or equal to 1, for example 0, and we try and plug it into f, we would get f of 0. Actually, let me write this down over here. F of 0 is the square root of 0 minus 1, which is the square root of negative 1, which is undefined. So we end up with a problem if we try and plug in anything that's less than 1. So in this case, for the domain of the composition, we have to say that x must be greater than or equal to 1. So our composition is going to be g of f of x equals x plus 1, and the domain is going to be all numbers greater than or equal to 1, which we can express on the number line as the interval from 1 to infinity, including 1. I want to address something quickly here. Sometimes students see this and they have an issue, because this looks like the domain should be all real numbers, but in the end we said the domain was from 1 to infinity. And the reason for this kind of glitch in the matrix is that This is a simplified version of the composition of functions. When we actually compose the functions, we ended up with this. The square root of x minus 1 all squared plus 2. When we simplified the square root of x minus 1, quantity squared, to just x minus 1, what we did was we ignored the fact that inside the radical, we need x to be at least 1 for this to be defined. And when we canceled these out, we end up with x minus 1. And these two things are only equal to each other when the first one is defined, which is specifically on this interval. So I'm going to write this out here. The square root of x minus 1, quantity squared, is only equal to x minus 1 when x is greater than or equal to 1, because otherwise this square root is undefined and the whole expression is undefined. So when we do something like square a square root, we're playing with fire as far as the domain goes, because we're starting with something that has a particularly restricted domain, x is greater than or equal to 1, and we end up with something that looks like it's true for all real numbers. This is why we need to specify the domain in our final answer, because if we don't, people might think that we can plug in any value of x and we're going to end up with x plus 1. But this composition only works for this domain.